So, we have this problem here. It's a scene from Mission Impossible Ghost Protocol. In this scene, Tom Cruise slides down this wire. Our concern is to check whether this is possible or not. If you are here from the short video, then you already know what the answer is. But one thing I can assure you is that at the end of this video, you will happily say that, damn, this was something interesting. You will learn how to apply bookish knowledge in real life. So sit down with your headphones and listen. We will solve this problem in three main parts. The first step is to find the equation of the path that is being traveled. Second, we will calculate the distance that he is shown to travel in the movie. And finally, we will draw a free body diagram of the problem and come up with a differential equation that will govern the motion along this wire as a function of distance traveled. To start with anything from mechanics, we must first know what is the exact path that is being traveled. We need to find the equation of this wire as our path. This wire starts from this window in this building. I found this ATM in this wall of this building on the Google Maps. So it's a good reference for height of this window, which is about 19.6 meters from the ground. Let's make the diagram. We have this left support 19.6 meters. This wire then travels across this length to the other side supported by another wire tied at this point on this building, and another end somewhere diffuses in this region, which is not clearly visible, but it's almost parallel, so it doesn't matter. We just need this height. I found this scooter parked beside this building whose dimensions are available on internet. After adjusting for the parallax a bit, the height of this building is 7.15 meters. And on the Google Maps, taking this building as a reference, running parallel, we get this height is 11.76 meters. From this position, this perspective is very much distorted, but it's almost halfway of both the lengths. So we get this height to the right support is approx 9.4 meters. I can see this wire goes here, where I assume it has been tied somewhere just for shooting purpose, but just leave it. Assume that it's a rigid support with a height of 9.4 meters. Now come to the wire. A freely hanging chain or a wire or anything continuous that is flexible enough due to its own weight, when holded from both the ends, forms a unique shape, and this shape is not a parabola. The name of this shape is given as catenary curve, and it is given by this cosine hyperbolic function. The lowest point on this curve is called the vertex. In this function, this parameter c tells us that how much is the vertex is above the x-axis or below the x-axis, and this d tells us that how much is it on the left or right of the y-axis. This parameter a is something regarding this catenary curve. It tells us that how much the curvature is bent. If a is too big, then curvature is less. If a is very small, then the curvature is very curvy, something like this. To find the equation of this wire, we need these three constants. Okay, one thing we can do to make things easier is just move our origin just below the vertex. Now we know the x coordinate of the vertex. We need to know the y coordinate of this vertex to get to know the equation of this curve. In this frame, if we draw the parallels and some geometry, after calculating the ratios of these equally length arrows, we have this height is approximately 8.044 meters. Now we have the coordinates of the vertex, and from Google Maps we have this horizontal span total length is 37.64 meters. Now let's assume that this distance is p. Now we can write the coordinates for the fixed endpoints. For the vertex, x coordinate is already 0, so we can use it to find the value of parameters in general equation of our curve. This is our equation, and because we have shifted our origin to y-axis, so this parameter d is already 0. We have the coordinates of a vertex. If we substitute y equals 8.04 and x equals 0 in this equation, we have this cos hyperbolic 0 is 1, so we can have c equals 8.04 minus a. We got c in terms of a. We can substitute it in our main equation, and our equation is left only in one parameter, that is a. Since this is the equation of our curve, it must pass through these endpoints. So these endpoints must satisfy this equation. Although in terms of p, if we put these vertices in our equation, we have these two equations in two unknowns, that is p and a. But a good thing is that these two equations are not just linear equation into variables. These have this hyperbolic cosine function there. So any conventional method that we have learned in school is not going to help us to solve this equation. So what we do? We go to a bit higher maths. We will use Newton-Raphson method to solve these equations. I have wrote down a Python code to solve these equations, and we have got the parameter a is 35.04 and p is approx 9.9. Now we have the equation of the path, and now we can find the length that is to be traveled to reach the vertex of this catenary. We have this curve, say y. We can divide its length into small pieces. Let's say one of such pieces is ds on it. We can draw a right triangle of height dy and base dx. By Pythagoras theorem, we have this ds equals root over dx squared plus dy squared. We can take this dx squared common out of it, and we are left with 1 plus dy over dx whole squared. And this dx can come out of the radical, and we are left with this beautiful expression. We know from calculus, for getting the total length of this curve between the bounds a to b, we can integrate this curve from a to b. In this integrand, we have this first derivative of y. For our curve, y equals a times cos hyperbolic of x by a plus some constant. its derivative will be a as it is. Derivative of cos hyperbolic of x by a is sine hyperbolic of x by a, and the derivative of x by a is 1 by a, thus a and a cancels out and the derivative of this constant term is 0. For our curve, a is 35.04, so put it, and we have to integrate this term. Here the upper limit is x coordinate of the vertex, that is 0. The lower limit a is the point where he jumps to hold on the wire. From this building, he jumps approximately 17 meters above the ground, whose x coordinate on the curve is approximately minus 24. So we can put this lower bound, and I am using this online tool for integration, which gives the length that is to be traveled to get down to the vertex is 26.54 meters. Now let's come to the dynamics. It's the most interesting part of this problem. Starting with his jump and keeping in mind the parallax error, he jumps approximately at 47 degrees from horizontal in the plane passing through this wire. The components of force due to jump will be in 3 axes, but we will assume that all the jump force is in his plane of motion. And as a fair assumption in his favor, we can assume that he is a good athlete and can jump a vertical height of 1 meter. And using kinematic equations, we have his initial jump velocity as 4.43 meters. Well, he jumps at an angle of 47 degrees. We can have again a fair assumption that the point he reaches by jumping is at his maximum height of jump. At maximum height, vertical component is 0. The horizontal component will be 4.4 times cos 47 degrees. And to find the component along the tangent to the curve, we can find the inclination of tangent at this point by differentiating our curve with respect to x, which comes out to be 37 degrees. So its component along the tangent is 4.43 times cos 47 degrees times cos 37 degrees, which is 2.4 meters per second. Now, let's come to its free body diagram. Consider this point on this curve. It has a downward force due to gravity, which is mg, and a normal force due to this wire. And because this motion is on a curved surface, so there will be a component of centrifugal force, which is mv square over r. And what this r is here, it's the instantaneous radius of a circle at a particular point on this curve, which is formally called the oscillating circle. We're going to calculate this radius very soon, but for now, we can resolve this mg into 2 components. One is tangential to this curve, which is responsible for the motion along this curve, and other component perpendicular to it is opposite to the normal force. There is one more force here that is acting against the motion of this point. This is frictional force. We are denoting it by F. Okay, so we have now all the forces acting on this body. Okay, from now this part is going to be very calculative. Those who are not interested can skip it, and those who are interested and want to know how things happen can continue. From Newton's second law of motion, we know that mass times acceleration is equal to the applied imbalance force that is causing the motion. Here, mass is just m. It is the mass of Tom Cruise. Acceleration is dv over dt. Now, here the force is all the force that is acting in this direction. That is mg sine theta minus the force that is acting opposite to it. That is friction force, which we can write as mu times n, where n is the normal reaction. And mu is the coefficient of friction between this belt and this wire, which is in the range of 0.2 to 0.4, but let's just take the average as 0.3. This normal force is opposite to the component of mg and the centrifugal force. So we can write this n equals mg cos theta plus mv square over r. We have got the zoomed out picture that will control the motion on this curve. Now we have to just make the things very precise by substituting them with words on the curve. So in this equation, let me tell you what this r is in the centripetal force. Let's say we have this arbitrary smooth curve in Euclidean plane. When a part of it is zoomed enough, it can be viewed as an arc of a circle of some radius. This circle is called the osculating circle. Formally, it is a circle that has the same tangent, plus it has the same curvature at this small portion of this curve. Its radius is called the radius of curvature. Let's say we have an arc whose tangent is inclined at an angle of 5 degrees from horizontal. Curvature measures how fast this tangent changes its direction with per unit change in arc length. Mathematically, curvature k is given by d phi by ds. It is the reciprocal of radius. This is how it is defined. So to find the radius, we need to find d phi over ds for our curve. And how do we do that? We need something that can relate phi and s. And how can we do that? We know a relation between trigonometry and calculus, that is tangent of phi is dy over dx, which we can write as phi equals tangent inverse dy over dx. If we differentiate it with respect to x, if you remember the derivative of tangent inverse x from your high school, we have d phi over dx equals 1 by 1 plus y dash squared times second derivative of phi. This is the relation between phi and x, but we needed a relation between phi and s. So we need something that can relate x and s. And for this, we have our arc length element ds equals root over 1 plus y dash squared times dx, which we can write as dx over ds equals 1 by root over 1 plus y dash squared. If we multiply these equations side by side, this dx cancels out, and if we substitute these values of y dash and y double dash in this expression, we have the instantaneous radius of our curve, which we can substitute in our equation. In this equation, this mass m is a constant, t is an independent variable. This variable v is dependent on t, it's the velocity. This g is again a constant, and we have this another dependent variable theta in these two places. This theta depends upon the position of Tom Cruise on this curve, which is needed to be expressed in terms of distance traveled, that is the variable x. And this mu is again a constant, so we have to compute this cosine theta and sine theta in terms of x. In this free body diagram, here we have two right angles, one this and another this. These two angles are vertically opposite, so this is also theta. So this total angle is 90 minus theta plus 90, which is 180 minus theta. From calculus, we know that tangent of this angle 180 minus theta is dy over dx, but tangent of 180 minus theta is minus of tangent theta, so dy over dx is minus of tangent theta. And we have computed dy over dx for our curve, which is sine hyperbolic of x by a. So all of these terms are equal to each other. Now we have just simple manipulations. We can write sine theta as tangent theta times cosine theta, because tangent is sine by cos and cos cancels out, so we are left with sine. We can write this cosine theta as 1 by secant theta, and secant theta again in terms of tangent theta, and we know the value of tangent theta in terms of x by a, so we substitute this value of tangent theta in denominator. This is 1 plus sine hyperbolic of x by a, which is cosine hyperbolic squared x by a. This radical will cancel the square, and we are left with this sine hyperbolic x by a by cos hyperbolic of x by a. For cosine theta, we can write cos as root over 1 minus sine squared theta, and we have just computed sine in terms of x by a, so we just replace it and little manipulations. We have cosine theta is 1 by cos hyperbolic of x by a. We can substitute both of these values in our equation back. Our expression is almost complete, but there is a problem here. This equation tells us the change in velocity with respect to time, but our concern is to check the change in velocity with respect to distance traveled, not time. So instead of this, we need change in velocity with respect to distance traveled. And how can we do that? It's simple. We can divide and multiply it by ds. Manipulating it, we have ds over dt, which is velocity, and we have this dv over ds. But instead of ds, we needed dx here. So we need to find an expression that can relate s to x. Now this is the third time we are going to use this. This is our arc length relation. ds is root over 1 plus dy over dx squared times dx, by which we get root over 1 plus sine hyperbolic squared x by a, which is an identity that is equal to cos hyperbolic squared x by a. This square and this radical cancels out. We get ds equals cos hyperbolic x by a times dx. Value of dx, substitute in this expression. We have this equation and we are left with just a final touch to it. We can cancel out this m from both the sides, and again we can cancel out the terms of cosine hyperbolic of x by a from both the sides. And if we take this v on right hand side, we have this beautiful equation that is telling us that how much our velocity is affected with the length traveled. It's a non-linear ordinary differential equation of first order and first degree, and we have our initial value of this equation of the jump velocity at x equals minus 24.54. We have velocity of 2.4 meters per second. Now there are ways to solve this equation, and we have a lot of them using numerical methods. We are going to use Runge-Kutta method of fourth order to solve this ODE. It will take a lot of steps to solve this equation, so I wrote a Python code to make things easier and precise, which gives he can travel a total distance of 29 meters, which is roughly 3 meters to the right of the vertex. And I was totally disappointed by the result that he actually can travel this whole distance. Yeah, maybe this belt may not be able to survive this long frictional, but I haven't computed that. Also some assumptions that I have made, but really I was totally disappointed when I computed that he can actually travel a distance of 29 meters. This is what it is for today, guys. Leave comments, leave whatever you want. I am traumatized. I was completely broke.